Welcome back to Atomic Insight. In today's episode, we're diving into one of the most fundamental mysteries of the universe, the atom, the building block of everything around us. From galaxies to living cells, nature builds complexity from simple structures. But what happens when we zoom all the way down to the smallest scale? Atoms were once thought to be indivisible. But what if that's not true? What if breaking an atom changes everything we thought we knew about matter? Do you believe that something so small could hold the key to understanding the entire universe? Before we begin, don't forget to subscribe to the channel and leave a comment below sharing your thoughts. We'd love to hear what you think. Structure, an inherent principle woven into the very fabric of existence. We witness its profound elegance everywhere, from the grandest cosmic scales to the most intimate cellular mechanisms. Consider the universe itself. The majestic, spiraling tendrils of galaxies, each a complex dance of billions of stars, or the mesmerizing regularity of planets tracing their predictable orbits around a central sun. Even within our own bodies, the double helix of DNA, a masterpiece of molecular architecture, meticulously carries the entire blueprint of life, a code for creation itself. This recurring pattern reveals a fundamental truth. Nature is a master builder. It constructs immense and astonishingly diverse structures not from an infinite array of unique components, but from the artful arrangement of a few, simpler constituent parts. Billions of stars are not random, but organized into galaxies. Countless planets and stars coalesce, bound by gravity, to form solar systems. As we progressively zoom inward, diminishing our scale of observation, this profound tendency persists. Nature's predilection for modular construction, utilizing a limited palette of simple building blocks to generate the breathtaking complexity and diversity of our universe. In this exploration, we embark on a journey to understand one of these foundational, incredibly small systems, the atom. Arguably one of the most fundamental systems in all of creation, the atom serves as our crucial starting point. While the concept of atoms often conjures images of indivisible particles, it's a fascinating paradox. Atoms can indeed be divided. However, this act of division triggers a truly extraordinary transformation, one that starkly differentiates it from the simple partitioning of larger samples of matter. Imagine, for instance, a gleaming bar of pure gold. You could saw it in half, creating two smaller, but still perfectly identifiable, bars of gold. You could continue cutting these smaller pieces into even tinier fragments, each still retaining the quintessential properties of gold. This process could theoretically continue, yielding increasingly minute samples of the element. But if we could somehow sustain this process indefinitely, beyond the reach of any physical tool, we would eventually arrive at a solitary, isolated atom of gold. Now what then? Is this lone gold atom truly the ultimate, uncuttable unit? Surprisingly, no. It can be further divided. Yet, the act of splitting this single gold atom is profoundly different from cutting a gold bar. When an atom of gold is divided, its very identity is shattered. The resulting fragments are no longer gold. They transform into something entirely new, losing the defining characteristics of the original element. This profound revelation naturally leads to a compelling question. If atoms themselves can be broken apart, what are they composed of? If they are divisible into constituent particles, then these particles must, by definition, be even smaller fundamental units of matter. And indeed, they are. Atoms are comprised of just three primary types of subatomic particles, each with distinct properties. Asterisk protons, asterisk positively charged particles. Asterisk electrons, asterisk negatively charged particles. Asterisk neutrons, asterisk particles possessing no electrical charge. Protons and neutrons are relatively hefty, possessing nearly identical masses. They reside together in an incredibly dense, compact region at the very heart of the atom, known as the nucleus. Orbiting this minuscule, positively charged nucleus are the much lighter, negatively charged electrons, their constant motion balancing the positive charge supplied by the protons, thus rendering the atom electrically neutral overall. Most of us carry a mental image of this atomic structure, a tiny, dense nucleus orbited by energetic electrons. But how did humanity arrive at this elegant and intricate understanding? The journey to uncover the atom's inner workings is a story as captivating and filled with intellectual triumph as the structures it seeks to explain. Our objective today is to unravel this fascinating narrative, to trace the discovery of each of these subatomic particles and witness how generations of relentless scientific inquiry, often building upon and sometimes overturning previous theories, ultimately converge to forge our modern understanding of the atom, the most fundamental building block of matter. The earliest glimmer of atomic thought emerged from the intellectual ferment of ancient Greece. Philosophers of that era, operating primarily through reasoning and deduction rather than empirical experimentation, proposed that all matter was composed of a select few fundamental substances. These substances, they posited, combined in various ways to create the myriad materials observed in the world. The Greeks widely recognized elements as air, water, earth, and fire, believing that the constituent particles of these elements were absolutely indivisible, or atomos, a term literally meaning uncuttable or indivisible. Thinkers like Democritus and Leucippus were the primary proponents of this atomistic view, though it faced strong opposition from figures like Aristotle, who favored a continuous view of matter. Of course, our modern understanding drastically differs. We now know that none of the Greek elements are true chemical elements, and, more importantly, that genuine elemental atoms can indeed be divided, albeit with transformative consequences. Nevertheless, the Greek term atomos proved remarkably resilient. It endured through millennia and is still the very word we use to denote the smallest quantity of a given element that can still retain its distinct chemical identity. Following the intellectual zenith of ancient Greece and its subsequent decline, Western scientific inquiry into the fundamental nature of matter entered a period of relative stagnation, almost a standstill. The vibrant philosophical debate regarding the atom faded into obscurity, replaced by other preoccupations. It wasn't until the dawn of the 19th century that the concept of the atom experienced a dramatic resurgence, thanks in large part to the groundbreaking work of an English chemist named John Dalton. Dalton operated in an era predating the sophisticated scientific instruments we take for granted today. He possessed no means to directly observe or manipulate individual atoms. What he did possess, however, was an exceptionally sharp intellect, a keen eye for meticulous observation, and the invaluable intellectual legacy of predecessors like Antoine Lavoisier, whose work on the conservation of mass laid critical groundwork. Utilizing relatively straightforward chemical experiments and careful measurements, Dalton was able to synthesize a profoundly sound atomic theory based on the empirical evidence before him. Let's delve into the kind of chemical reactions Dalton might have meticulously conducted and observed. Imagine a molecule of gaseous oxygen. We then introduce two molecules of gaseous hydrogen, initiating a reaction. The outcome is familiar: the formation of water, a relatively simple chemical transformation. Dalton could have carefully measured the precise quantities of his starting materials, reactants, and his end products. For instance, he might have found that when 32 grams of oxygen reacted completely with 4 grams of hydrogen, exactly 36 grams of water were produced. This observation perfectly illustrates the law of conservation of mass, a principle famously articulated by Lavoisier. The total mass of the reactants always equals the total mass of the products in a closed chemical system. 32 plus 4 is equal to 36. This law strongly implied that matter was simply being rearranged, not created or destroyed. Now, consider a slightly different scenario. Dalton could also react oxygen with hydrogen, but this time, he might find that one oxygen molecule reacts with only one hydrogen molecule, leading to the formation of a different compound, hydrogen peroxide. In this instance, perhaps 32 grams of oxygen combine with 2 grams of hydrogen to yield 34 grams of hydrogen peroxide. Again, the law of conservation of mass holds true. 32 plus 2 is equal to 34. These consistent observations, where the total mass remained constant, were foundational to Dalton's thinking. But there was another, even more crucial observation that provided the linchpin for his atomic theory: the law of multiple proportions. Let's revisit our two reactions. In the formation of water, 32 grams of oxygen react with 4 grams of hydrogen, establishing a mass ratio of oxygen to hydrogen of 8:1, or simply 8, if we fix hydrogen at 1 unit. In the formation of hydrogen peroxide, 32 grams of oxygen react with 2 grams of hydrogen, yielding a mass ratio of 16:1. Notice something remarkable. These two ratios, 8 and 16, are not arbitrary. They are simple whole number multiples of one another. 16 is precisely twice 8. Dalton observed that whenever two elements combine to form more than one compound, the masses of one element that combine with a fixed mass of the other element are in ratios of small whole numbers. You might observe a ratio of 8 or a ratio of 16, but never, for example, 12. This elegant mathematical relationship, combined with the law of conservation of mass, provided Dalton with an unassailable argument for the existence of discrete, indivisible particles, atoms. He reasoned that if matter were continuous, these simple whole number ratios would be inexplicable. However, if elements were composed of individual atoms that combined in fixed, whole number ratios to form compounds, then these observed mass ratios made perfect sense. Dalton's genius lay in synthesizing these macroscopic chemical laws into a coherent, microscopic explanation. His atomic theory provided the only plausible framework for understanding these seemingly disparate observations, finally lending rigorous scientific weight to the ancient Greek philosophical notion of atoms, rekindling a concept that had lain dormant for centuries. Dalton himself articulated his conviction with clarity, stating, "Matter, though divisible in an extreme degree, is nevertheless not infinitely divisible. That there must be some point to be reached beyond which we cannot go in the division of matter. I have chosen the word atom to signify these ultimate particles." To Dalton's mind, these atoms were the ultimate, indestructible, solid spheres, the fundamental, indivisible units of matter. He believed he had reached the very end of the line, discovering the atom as the irreducible building block. However, scientific progress rarely ends with a definitive period. It often builds upon, refines, and sometimes dramatically reconfigures previous understandings. It would take another full century, a period marked by astounding technological advancements and new experimental techniques, before humanity's understanding would catch up with the realization that the internal workings of nature's wondrous creation, the atom, were far more complex. It relied not on an indivisible sphere, but on a predictable and intricate combination of even smaller entities, what we now call subatomic particles. The first major breakthrough in peering inside the atom arrived through technology that, ironically, dominated living rooms for decades. Most of us are familiar with the image of the large, heavy, cube-like television sets that graced homes for much of the late 20th century, before finally giving way to the sleek, energy-efficient flat-panel displays that now adorn our walls. Yet, the foundational technology behind these seemingly dated appliances, the cathode ray tube, CRT, was conceived much, much earlier, in the late 19th century. And it was this simple, yet revolutionary, device that played a pivotal role in advancing our comprehension of the atom. Consider J.J. Thomson's innovative use of the cathode ray tube. It consisted of a straightforward, evacuated glass tube containing two metal discs. Each disc was connected to a terminal of a high-voltage battery, establishing an electric potential across them. The negatively charged disc was termed the cathode, and the positively charged disc, the anode. When this apparatus was energized, a mysterious, glowing beam was observed traveling from the cathode towards the anode. Thomson, ever the meticulous experimenter, ingeniously designed an anode with a small hole in its center, allowing this beam to pass through and continue traveling along the length of the evacuated tube, allowing for undisturbed observation. Initially, the beam appeared to travel in a perfectly straight line, but Thomson's crucial experiment involved introducing external electric fields. When he placed additional charged plates above and below the tube, he observed a subtle, yet unmistakable, deflection of the beam. Critically, the beam consistently bent towards the positively charged plate. This observation provided Thomson with two profound insights into the nature of his cathode ray. Firstly, the beam had to be composed of negatively charged particles, as it was attracted to the positive plate. This direct evidence of negative charge led him to christen these novel particles electrons. Secondly, and perhaps even more groundbreaking, the degree to which the beam curved under the influence of the electric field allowed Thomson to estimate the mass-to-charge ratio of these particles. He reasoned that heavier particles would be less easily deflected by the electric field than lighter ones. Using this ingenious cathode ray tube, JJ, Thomson was able to isolate and produce pure beams of electrons, meticulously measuring their mass, velocity, and charge. His painstaking measurements culminated in a truly astonishing conclusion. The electrons in the cathode ray were not only negatively charged, but they were also significantly smaller than atoms themselves. This discovery shattered Dalton's long-held model of the atom as an indivisible, solid sphere, forcing a radical re-evaluation of matter's fundamental composition. With the atom's indivisibility disproven, the scientific community now faced a monumental challenge: to conceive of the atom's internal structure. More than a century after Dalton had breathed new life into the atomic concept, Thomson stepped forward to propose the very first structural model for the atom. He theorized that atoms were not solid, homogeneous spheres, but rather complex entities comprising tiny, negatively charged electrons. He envisioned these electrons as being sparsely embedded within a much larger, lower-density, positively charged spherical matrix. This positive pudding accounted for the vast majority of the atom's mass and ensured its overall electrical neutrality. This conceptualization gave rise to the iconic plum pudding model, where the electrons were likened to raisins scattered throughout a positively charged pudding. It was a bold and necessary first attempt to reconcile the newly discovered electron with the known properties of atoms. However, scientific models are rarely the final word; they are stepping stones. Thomson's plum pudding model, though revolutionary, proved to be remarkably short-lived. Less than 2 decades after its proposal, one of Thomson's own brilliant protégés, Ernest Rutherford, embarked on a series of experiments. Initially, Rutherford intended to further elaborate on Thomson's model, but his groundbreaking findings would, instead, utterly dismantle it. Rutherford is widely credited with the discovery and characterization of alpha particles. These are positively charged particles, significantly larger, indeed, over 1,000 times more massive than electrons. Alpha particles are naturally emitted during the radioactive decay of heavy, unstable elements such as uranium. While the discovery of these particles was significant in itself, Rutherford's enduring fame stems not just from their discovery, but from the ingenious way he subsequently employed them to probe the very heart of the atom. Rutherford's insatiable curiosity compelled him to investigate how these powerful alpha particles would interact with, and thus reveal, the hidden internal structure of the atom. The relatively large and energetic alpha particles were precisely the tools Rutherford needed to interact with atoms. His experimental setup was both elegant and insightful. He directed a focused beam of these powerful, positively charged helium nuclei at a remarkably thin sheet of gold foil. Encircling this foil was a specialized fluorescent screen, typically coated with zinc sulfide, designed to emit a tiny flash of light, a scintillation, whenever struck by an alpha particle. Based on the prevailing scientific understanding of the atom at the time, specifically J.J. Thomson's plum pudding model, Rutherford's team expected a rather uneventful outcome. Thomson's model envisioned the atom as a diffuse sphere of positively charged matter, much like a pudding, with negatively charged electrons, the plums, embedded within it. According to this model, the alpha particles, being much heavier and faster than electrons, should simply slice right through the thin gold atoms, experiencing only minimal, if any, deflection due to the widely dispersed positive charge. They anticipated that the vast majority of alpha particles would pass directly through the foil, perhaps being scattered by only a few degrees. As the experiment unfolded, Rutherford initially observed what was expected. The brightest spot of scintillations appeared directly behind the gold foil, indicating that most alpha particles had indeed passed through largely unimpeded. However, his astonishment, and indeed that of his assistants Hans Geiger and Ernest Marsden, was palpable when they widened their scope of observation. When they directed their attention to the outer edges of the screen, further from the direct path of the source beam, they began to see something utterly unprecedented. A tiny fraction of the alpha particles, incredibly, were being deflected at extremely large angles, some even bouncing almost straight back towards the source. This observation was nothing short of revolutionary, completely shattering the plum pudding model. If the atom's mass and positive charge were distributed uniformly throughout its volume, there was simply no way for an alpha particle to be reflected so violently back towards its origin. Such diffuse matter wouldn't possess the localized electric field strength required to exert such a powerful repulsive force on the fast-moving, positively charged alpha particles. It was like expecting a cannonball to bounce off a cloud. Rutherford's results forcefully indicated that atoms must be mostly empty space, but critically, with an extremely concentrated, positively charged nucleus at their core. This nucleus, though occupying only a minuscule fraction of the atom's total volume, contained almost all of its mass. This single, dense point of matter was the only thing capable of causing the rare, head-on collisions that resulted in the dramatic backscattering of the alpha particles. Rutherford himself, famously articulate and prone to vivid analogies, perhaps best described the sheer incredulity of his discovery. "It was quite the most incredible event that has ever happened to me in my life. It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you." Indeed, to explain these profoundly dense, rebounding alpha particles, there simply had to be an extraordinarily dense, yet vanishingly small, point of mass at the atom's center. This tiny, concentrated core would be dense enough to repel the alpha particles, but its minute size would explain why only a handful of them ever ricocheted during the experiment. Rutherford concluded that atoms were predominantly composed of empty space, with a minute, dense nucleus at their core. His revolutionary Rutherford model, sometimes dubbed the planetary model, due to its depiction of electrons orbiting a central nucleus, was the first to accurately recognize that the vast majority of an atom's mass resides within its small, dense nucleus. Thus, Rutherford had discovered the nucleus, a dense, positively charged core, encircled by much lighter, negatively charged electrons. But just how incredibly tiny is a nucleus? Let's recall that we've already learned how small atoms are, with diameters of approximately 100 picometers, roughly 1/10 of a nanometer. Rutherford's groundbreaking work ultimately led to the discovery that a typical nucleus has a radius of only about 100,000th of its electron cloud. This is in the realm of a femtometer. 1 fm equals 10 to the power of negative 15 meters, or 0.0000001 nanometers. To put that mind-boggling scale into perspective, imagine an atom stretched across the entire width of a football stadium. In such a colossal atom, its nucleus would be no larger than a grain of sand at the very center of the field. Or, if we were to inflate an atom to the size of the Earth, its nucleus would be roughly the size of a single large building in the city center. If you were an electron orbiting such an Earth-sized atom, your orbit might extend all the way out to Pluto. And looking back at the nucleus at the center, it would appear as nothing more than a faint speck of light, perhaps the size of our own sun, in the vast distance. Rutherford had determined that massive, positively charged particles were concentrated in the atom's center, the nucleus. The proton itself, the fundamental positively charged particle within the nucleus, had been effectively discovered through these insights. However, there was still one last piece of the atomic puzzle to fall into place. As research continued, particularly in the realm of radioactivity, there were some observations about atomic nuclei that simply didn't quite add up. Literally. Specifically, researchers had been bombarding beryllium with alpha particles to produce a new, mysterious type of radiation. Crucially, this radiation did not recoil from the nuclei it struck in the same way Rutherford's alpha particles did. Instead, these new particles smashed into them with tremendous force, deeply penetrating the nuclei and knocking out protons from the target atoms. Understanding these unusual observations became possible in 1932, when James Chadwick, a former student of Rutherford's, completed the list of fundamental subatomic particles. Chadwick reasoned that this newly discovered radiation was able to penetrate other atomic nuclei so effectively precisely because it was uncharged. In contrast, the alpha particles used by Rutherford carried a positive charge and were therefore repelled by the positively charged nuclei they encountered, explaining their tendency to ricochet and bounce back. But these new particles, though massive enough to cause significant impact, were able to delve deep inside the nucleus without being repelled. They had to be free from electrostatic repulsion. Chadwick performed meticulous experiments to confirm this, allowing these neutral particles to strike nuclei with great force. He then estimated their mass and dubbed these particles neutrons. Quite interestingly, Chadwick found that these neutrons were almost identical in mass to protons, being just a tiny fraction of a percent larger. Because protons and neutrons are very similar in mass, and both are vastly more massive than electrons, they together contribute almost all of an atom's mass. For convenience, chemists use a specialized unit of mass called the atomic mass unit, AMU, when comparing the masses of atoms to one another. Protons and neutrons themselves each weigh approximately 1 atomic mass unit. This very convenient unit of measurement leads to nice, round numbers when communicating the mass of individual atoms. By 1932, the combined insights of the ancient Greeks, Dalton, Thomson, Rutherford, and Chadwick, along with countless other contributors, had led us to a remarkably sophisticated understanding of atomic structure. This model largely resembles the popular depictions of the atom you see today. Let's begin with the simplest atom, that of the element hydrogen. All atoms, as we now know, consist of that dense, central core of matter called the nucleus. And within that nucleus, we invariably find one or more protons. In the case of hydrogen, around that dense, positively charged core, we find our electrons. To balance the single positive charge from the proton in the nucleus, a complete hydrogen atom has just one electron orbiting it. We sometimes refer to this version of hydrogen as protium, because its nucleus contains only a single proton. Now, don't let the scale here deceive you. For clarity and ease of viewing, I've vastly exaggerated the size of the nucleus in this illustration. If atoms were truly this size, their nuclei would indeed be no larger than a grain of sand. But for us to see what's happening, I've magnified it. It is the count of protons in the nucleus that gives an element its unique identity. If I add a neutron to my construction here, I still have hydrogen. But now, my hydrogen atom has roughly twice its original mass. We call this type of hydrogen, which also contains a neutron, deuterium. It is more massive than protium. I can further increase the mass of deuterium by adding yet another neutron to obtain what we call tritium, another form of hydrogen. Tritium is 3 times more massive than protium. So, these 3 atoms are all hydrogen, but they clearly differ from one another through their masses. When we have a situation like this, we refer to these groups of atoms as isotopes of one another. Therefore, protium, deuterium, and tritium are all isotopes of hydrogen. Their chemical properties will be very similar because they have the same number of electrons, even though their atomic masses differ significantly. We sometimes distinguish them by writing a superscript number with their elemental symbol to indicate the mass of the isotope in this case. Hydrogen, 1 for protium, hydrogen, 2 for deuterium, and hydrogen, 3 for tritium. Now, let's focus on tritium and add another proton to the nucleus. This fundamentally changes the identity of our atom. When I add another proton to the nucleus, I must also add an electron to its electron cloud to balance the charge. We now have a completely new element because the number of protons in the nucleus has changed. We've taken our first step across the periodic table. Add yet another proton and an electron to balance it, and we form an atom of helium. Continue adding protons and electrons, and we move to lithium, 5. But the most common isotope is lithium, 7, with 2 additional neutrons. Another proton, another neutron, and another electron gives us beryllium, 9, and so on. We can estimate the atomic mass of an isotope of an element simply by adding the number of protons and neutrons in that particular isotope. For example, a carbon atom will always have 6 protons. So if I want to talk specifically about a carbon atom with 6 neutrons in its nucleus as well, I would write its elemental symbol like this, C12 or carbon 12. This is the most stable isotope of carbon. If, instead, I have carbon with 7 neutrons, its mass is 6 plus 7, or 13, making it carbon 13. And again, I can add one more neutron to get 8. So now I have a total of 14 particles in the nucleus, for a mass of 14. This is the famous carbon 14 isotope, which is used in radiometric dating in archaeology. This notation can be used for all elements. Take a look at uranium, for example. All neutral uranium atoms will have 92 protons and 92 electrons to balance that charge. Add 143 neutrons, and you have uranium-235, a relatively rare isotope of uranium that is highly unstable and can split apart instantaneously, making it useful for constructing nuclear weapons. Add just 3 more neutrons, and you get the isotope uranium-238, an isotope that is also radioactive but decays so slowly, over billions of years, giving us a natural clock by which to measure the age of the Earth itself. Many elements exist in nature as 2 or more isotopes. In fact, most of them do. And when this is the case, the periodic table will report an average mass for a given element. For example, in nature, you can see that chlorine atoms exist as 2 different isotopes. Chlorine, 35, which is roughly 75.8% abundant in nature, and chlorine, 37, which is approximately 24.2% abundant. A quick look at the periodic table shows us that if we consider a large collection of chlorine atoms, knowing the relative populations and the masses of the isotopes that make it up, the average mass of a chlorine atom is 35.45 atomic mass units. As the table reports, this doesn't mean there's a fraction of a particle in the nucleus. It simply means there are multiple isotopes that are abundant in nature. So far, our discussion of atoms has been limited to situations where the number of protons and the number of electrons are precisely the same. This is convenient because their opposing charges remain balanced, resulting in an overall neutral atom. But what happens when they are not balanced? As you might expect, when the numbers of protons and electrons are out of balance, we create a species that carries a net overall charge. These charged species can have properties that are dramatically different from their corresponding neutral atoms. Chemists call these charged atoms ions. In general, if there are excess electrons, we get a negatively charged ion, which is called an anion. If, instead, there is an excess of protons, we get a positively charged ion, which we call a cation. For example, let's look at the element fluorine, with 9 protons and 9 electrons. Fluorine looks something like this. But if we add an extra electron to it, we get what is known as the fluoride ion, an additive sometimes included in the water you drink or toothpaste to help strengthen your teeth. We can create an ion with even more charge by adding even more electrons. For example, consider oxygen. If we add 2 electrons to oxygen, we get what is commonly called an oxide ion. This is the form of oxygen that we find, for instance, in rusty metal. Now let's take a look at sodium, with 11 protons and 11 electrons. We can remove an electron from sodium, creating a positively charged sodium ion. This charged sodium ion is not the neutral sodium atom that your doctor keeps telling you to cut down on in your diet. That's the highly reactive metal. The ion is what makes up table salt. And just like cations, ions can take on higher charges when the discrepancy between electrons and protons is greater. For instance, magnesium would have 12 electrons in a neutral atom, but when found in rock-forming minerals like limestone, magnesium atoms are often missing 2 electrons, forming a cation with a +2 charge, Mg2+. So, let's take a moment now and review what we've discussed so far. We began by considering how nature uses a combination of small, simple components to create tremendous diversity across a wide range of scales, from galaxies to biological systems. We saw how atoms are not so different, having only 3 fundamental components called subatomic particles: protons, neutrons, and electrons. We saw how protons and neutrons reside in the atom's center, in its nucleus, giving the atom most of its mass, and how electrons balance out the positive charge from the protons in the atom's center. We then talked about the ancient Greek philosophers and their debates about the most basic component of matter, which led to the coinage of the word atomos, meaning indivisible. We saw how this word falls short in describing atoms as we know them today, but its profound history has prompted us to retain it as the name for the fundamental building blocks of elements. We took a look at how John Dalton's work reignited discussions about atomic theory, first proposed over 2,000 years earlier, and how he did this by considering the law of conservation of mass and the law of multiple proportions. We then saw how J.J. Thomson's work led to the discovery of the electron and the plum pudding model of the atom, and how his protege, Ernest Rutherford, by bouncing alpha particle radiation off of gold foil, concluded that atoms were actually composed of a dense nucleus of protons. 2 generations later, we saw how James Chadwick discovered the neutron, investigating this unusual type of radiation that didn't bounce off atomic nuclei, but instead penetrated them. Once we had our complete list of subatomic particles, we then delved deep into the structure of the atom itself. We saw how the number of protons gives an atom its identity, and how we refer to the number of protons in a given element as the atomic number. We then saw how the number of neutrons can affect the mass of an atom, generating what are called isotopes. We saw how the number of protons and neutrons together is called an isotope's atomic mass, or mass number. And finally, we saw how by adding or removing electrons from an atom's electron cloud, we can impart an overall charge to them, forming positively charged cations or negatively charged anions. But what neither Thomson nor Rutherford could possibly have known in their days is that the cloud of electrons around a nucleus is far from uniform. It actually involves a very complex system of electron orbitals, and the position of an electron within an atom's cloud or an ion is one of the most important driving factors in how these elements behave. Next time, we are going to dive deep into this intricate structure and investigate the electronic configuration of the atom. And that brings us to the end of today's journey into the structure of the atom, from ancient philosophical ideas to groundbreaking scientific discoveries that revealed protons, neutrons, and electrons. It's incredible to think that everything we see is built from just a few tiny particles, arranged in different ways to create the vast complexity of our world. What do you think about this idea? Does it change how you see the world around you? If you enjoyed this video, don't forget to subscribe to Atomic Insight and share your thoughts in the comments below. We'd love to know your perspective. Thanks for watching, and we'll see you in the next episode.